This video continues the discussion of pointers for my Principles of Data Abstraction class using C++. And in this video we're going to start talking about arrays and the relationship between arrays and pointers. So last time we learned the syntax for dereferencing. We also saw that the bracket notation was a way of dereferencing things. And now we want to put this inside of something that's explicitly using arrays. I'll make a new file for that. Include IOStream. And create our main. Okay, so how can we create arrays in C++? Well, the simplest way is with a static array. Now, something to note is that while I'm going to show how we can make arrays, it turns out that in modern C++ you probably shouldn't do this, at least not very much. There are going to be some assignments in the class where you will have to use dynamic arrays, and so I'm going to cover this here because it is essential for those assignments. But in general, for your programming, you're going to use the collections that are part of the standard library. Things like vector, and there's actually an std array that you should use over the default C style arrays in most cases. So how can I declare, say, an array of 10 ints? Syntax for that looks like this. This says that we're making an array that has 10 elements in it, and it is of ints. And we could stick values in there if we wanted. It's worth going ahead and compiling and running to see what happens when we print this out. Hey, you know what? That looks really familiar. That is the same type of pointer that we saw previously when we had stack allocated values. And that's exactly what this is. So when you create an array like this, you wind up getting a chunk of memory that is big enough, in this case, to hold 10 integers. It is a single contiguous block that is 10 times the size of an integer. I've mentioned size of. Let's make sure that you realize that there is actually an operation in C++ that you can use to get the size of things. So for example, an int on this machine uses 4 bytes. And so this is going to create a chunk of memory that is 40 bytes long. Okay, I say 4 bytes. Technically this is 4 times the size of the char. I just happen to know that this machine has a char that is 1 byte in size. So this is going to be 40 bytes in length. And indeed, it's an interesting question. What is the size of ARR? This array that we have just declared. And it says, sure enough, 40. Okay, that's all great. Very nice. What happens if we pass this into a function? Well, void now we'll go ahead and type this in the way that might feel right to you. For int I equals 0, I less than 10, plus plus I, a sub I equals I. Why? Just because we have something happening in there. And that runs and that compiles. what does this say for, oh, I didn't actually call it. Now that's interesting, isn't it? Okay, when I do the size of A, so I passed in this array, ARR, it was declared right here. The size of ARR is 40. We have a very good argument for why this is 40. We pass it into a function. I call the size of it here, and I get 8. Where did that 8 come from? Well, it turns out that 8 is exactly what we get if we print the size of an int star. This is a 64-bit machine, and so pointers require 8 bytes. And sure enough, when you pass an array into a function, the size of no longer tells you how big it is. This is one of the problems with arrays. Basically, all that's being passed in here is a pointer, and that's what the size of gives us. The fact that we told this that it's sub 10 really isn't significant. Okay, code compiles and runs just fine if I change this to be a pointer. And that's effectively what we're dealing with here. Both ARR, in fact, so I'm printing out ARR. What happens if I get the address of ARR? Well, since ARR is a pointer to a memory location, when you call the address of operator on it, it gives you the exact same value that you get with just ARR. Okay, so this is a fixed array. And as I said earlier, you probably won't be using these all that much. You really shouldn't use them all that much. There is a type called array that's in the standard library, and so we could pound include array and use that. I'm not going to go into that here. And it has numerous advantages, one of which is the array actually is going to remember how long it is, whereas these arrays really are just pointers to chunks of memory. But this has to be a fixed chunk of memory. What if I didn't know how big I wanted this to be? What if we were going to put in some horrible grammar here, and size equals, we'll start with actually just size, cn size not happy. Oops, darn, it's unhappy for the wrong reasons. Okay, they have support for this in GCC. It is not normally supported for C++. It is supported in C, but not in C++, and it appears that GCC has added it. You really shouldn't do this, though. There's also the problem that your stack size is limited. This array goes onto the stack if you wanted a really big array. The other issue is the fact that if I need this array to survive longer, so let's say the array were being declared up here inside of this function, and I need it to survive longer than the function, this is only going to last for the time that the local variable lasts, because it would be allocated on the stack. Generally, when you do dynamic arrays, you're going to do them on the heap. And this, like I said, you're going to use this for some of your assignments. So how do we make a dynamic array on the heap? So I could create this and start off as null pointer for null, or let's just go ahead and make a new int sub whatever size we just created. This will allocate that array of the particular size, and we need to, as we've seen previously, if we call new, we need to call delete. there are actually two forms of delete. There is the regular delete that we did previously, and there is the delete with brackets. And technically there are two forms of new. If you have new here with brackets, you need to call delete with brackets. If your new did not have brackets, your delete should not have brackets. It's very significant that you follow that rule. Calling delete with brackets on something that didn't have brackets, or messing it up the other way, can have very bad consequences for your code. Things will not be deallocated appropriately, and it can cause very interesting and challenging to find bugs in your code. So we'll just make sure we save that and compile. This is how we could make this is how you should make dynamically sized arrays in C++. We'll come back in the next video. We'll talk about why it is that you want to use new instead of malloc. It turns out that malloc from the C library still exists, but you really shouldn't be using it for C++ unless you're doing something that's quite esoteric.